So as I mentioned earlier there, what we're going to do here is we're going to continue lecturing so that we could cover definitely, we almost covered all of the hybridization part. We'll also talk about molecular polarity here next. And again, that should sort of set you up to obviously be able to complete the study assignment that we started yesterday, which should be study assignment B, involving pretty much all this stuff from chapter 3 and chapter 4. But I did want to kind of finish up, those topics so that you can complete that. All right. So, excuse me. We're going to continue sort of talking here first up about hybridization. We'll look at a few more examples of actual sort of Lewis structures and sort of where the electrons go and the bonding, including sigma bonds, pi bonds, and all those type of things as well. And then we will get into, as I mentioned, sort of molecular polarity. And again, like I said, that should sort of set you up pretty good for the remainder of that study assignment. So in lecture there, we just kind of finished up, kind of addressing really how to classify or assign hybridization to atoms. And really, again, just to emphasize sort of the relationship of what it's related to in terms of the Vesper model that we've been talked about previously. Really, hybridization is tied to the electron pair geometry name, as we were talking about. So it really is tied to that electron pair geometry. And really, just like you sort of count electron pair geometry in terms of electron pairs when you draw a Lewis structure, that's really the same sort of approach that you want to do when you're assigning hybridization. So same rules apply as I mentioned earlier today. If you're doing double bond or triple bond, we only count that as one electron pair. So really the number of electron pairs is really what you're looking for. And again, it doesn't matter if they're bonding electrons, non-bonding electrons. So in the sense of your Lewis structure, doesn't matter if they are dots or lines, you're just looking for the total number of electron pairs. And like I've said many times earlier today, this is like really sort of the easiest way really to assign hybridization is really just to count it off. And the number of electron pairs directly relates to what the hybridization of that particular element will do in that situation. So as we saw, just to kind of put them all together here, electron pair geometry of linear basically means that you have two electron pairs around the atom. And again, two electron pairs basically means always starting with S, you're going to get to an S and a P, which means that guy will go through sp hybridization. The next sort of electron pair geometry is trigonal planar. And if you remember trigonal planar, which is really our triangle type of geometry, that's our 120 degrees sort of bond angle, right? Will get us to 3 electron pairs. So again, if we started at the bottom here, an S, a P, and one more P would basically be 3, and that would be sp2 hybridization. That particular element would go through if you drew a Lewis structure that had that arrangement. Next one is basically tetrahedral. And tetrahedral, right, is basically that 4 electron pairs, that 109.5 sort of geometry. And again, if you just count it off, starting with the S, P, P, and one more P. Again, you did an S basically and 3 Ps. That will give you an sp3 hybridization. And again, like we saw earlier today, that sp3 hybridization may include in these hybrid orbitals both sort of bonding electrons, right, and also non-bonding electrons. So those lone pairs also are accounted for in these hybrid orbitals. So like we saw with NH3, there was basically a box that contained 2 electrons in it to begin with when it went through hybridization. And again, those basically correspond to the non-bonding electrons that we see around the nitrogen. Then we get into sort of our expanded octet, or exceptions to the octet rule, and we had our triangular bipyramidal. And that basically is 5 electron pairs. And again, if we start at the S and just keep counting, 1, 2, 3, 4, and that now gets us into our d orbitals. And again, that does make sense based on what we've been talking about, that, you know, really for these guys to sort of go through that expanded octet, they have to have those d orbitals available to them. So it would make sense that obviously if we get into that expanded octet situation, we're dealing with some d orbitals sort of happening. And really, you could just count it off like we did before, which would be sp3, and now we're adding our d. And the last one that we'll come across, which is octahedral, which is 6 electron pairs. Also, again, an expanded octet going 1, 2, 3, 4, 5. And obviously, we need to add one more d to it to get into there, and that would be sp3d2. So again, hybridization of the atom basically tied to, as you can see here, the electron geometry or electron pair geometry that we talked about. Again, not the molecular geometry. So, and we see that clearly that is not tied to the molecular geometry when we look at actually the 3 examples that we looked at. If you look at methane, if you look at ammonia, and we look at water, all 3 of these guys have different molecular geometry, right? This guy is tetrahedral for the molecular geometry. This guy is trigonal pyramid for the molecular geometry, and this guy is bent or V-shaped for the molecular geometry. So again, the hybridization not tied to the molecular geometry, but what they all share in common is the same electron pair geometry, how the electrons are arranged. They all have the same electron pair geometry. They're all tetrahedral. This guy is tetrahedral. This guy is tetrahedral. And obviously this guy is tetrahedral in terms of the electron geometry, right? So it is tied again to the electron geometry. And as we saw with our hybridization sort of arrows and stuff like that, because it's tied to the same electron geometry, hybridization again accounts for those non-bonding electrons as we saw. And again, those were the hybrid orbitals that basically, as it went through hybridization, ended up with 2 electrons in it to start with. So again, it accounts for all that. So hybridization tied to the electron pair geometry, not the molecular geometry. Any questions on that there? Now, I will say that I personally, these 2, we'll just talk about these 2. Sometimes this question comes up. I personally write it like this, and a lot of books do write it like this. But you will see, you will sometimes see these or this hybridization written like DSP3 or D2SP3. So you'll sometimes see it written with the D guys coming first. I personally don't do it that way. I do it this way. I believe your book does it this way. I'm not 100% sure, but some books will kind of do it this way. Some books will do it that way. Technically speaking, you can do it either way. I personally go with this approach. So in case you do see this, it is used by people in terms of the hybridization of these sort of expanded octets, kind of writing the D part first. It's just a different way of noting it, and it has a little bit to do probably with the energy factors of these guys. But so for us though, but you can't go sp3d, sp3d2 is perfectly fine. But I just wanted to note that, you know, you will sometimes sort of see these guys written like this in certain books and in certain ways. Any questions on the hybridization part here? Again, we're going to look at some examples here and just to make sure it all sort of sinks in. But, you know, what you need to be able to do is not necessarily draw all the arrows and stuff like that like we've been doing, but you do need to be able to draw the Lewis structure and be able to identify the hybridization of an atom. And again, the simplest way to do that is sort of what we were doing here. No, yeah, so you don't include the number. So the question is, do you include the number for the hybridization? So I'm assuming by number you mean that it's basically 4 atomic orbitals that are being hybridized. So you would not include that. So if you were asked for each of these guys here, basically, let's go with blue. For each of these center guys, they basically have 4 electron pairs. So if you're asked what is the hybridization for the carbon, you would write only sp3. It would be the correct answer. So you wouldn't put any number in front of it. sp3 implies that there's 4 hybrid orbitals that have been made. Basically, if you just count the letters, an S and 3 Ps implies 4 basically, and that 4 atomic orbitals were made. So that would be the correct way to answer that. Same thing for the nitrogen here. Again, it has 4 electron pairs. If you're asked what is the hybridization of the nitrogen, you would write sp3. And the same thing here with the oxygen, also has 4 electron pairs. You would write the hybridization for that guy as sp3. Yeah. So you wouldn't include any other sort of number in front of it. So when you're asked for hybridization, it really should be one of these answers here, either sp, sp2, sp3, sp3d, or sp3d2. That's really the only things in terms of what you should write in terms of that. Other questions on that? Okay. Now, in addition, we also talked about, towards the end there, and we're going to kind of see it here with some Lewis structures and hybridization and sort of the bonding that's happening. We talked about kind of 2 types of sort of bonds that occur between these orbitals, and when orbitals come together. And again, the difference, or what we were talking about, is the difference between sort of how they come together is basically that how they overlap with each other. So when we do again have really 2 orbitals, whatever shape they are, and they basically just go straight at each other, and they're on the same sort of axis in 3-dimensional space, and basically just run right into each other. That again is what is sometimes referred to as head-to-head overlap. And again, the idea here is the overlapping region is where we're seeing the sharing of electrons basically occurring. And this head-to-head overlap is what's known as a sigma bond. Again, sometimes abbreviated with the sigma symbol, like that guy. The guy in the parentheses is the symbol. And as I sort of oversimplified it maybe, but that's a good way of thinking about it. You really can think about a sigma bond as when you're sort of drawing your Lewis structures, kind of like a single bond, really. Kind of like the first line that you draw typically will be a sigma bond, and it will result in those orbitals really being pretty much centrally located to each other in the same sort of orientation, and their ability basically just to come straight at each other and come together. And that's different than what we see when we start sort of building out more than a single bond, when we start building out sort of double bonds and triple bonds and stuff like that. So when we deal a double bond, as I mentioned earlier, again, you could keep it pretty simple. You typically would draw obviously 2 lines. And again, that first line you could think of as almost like the single bond component of it. And that is going to be a sigma bond. But then we have some more orbitals that are going to overlap in sort of a pi bond situation. And you can think of that as sort of making your sort of second line, within your double bond situation. And again, the difference here between sort of how the sigma bond would overlap, like we have here, and the pi bond is really going to come from those unhybridized p orbitals. So these are these unhybridized p orbitals, and these are just, you know, regular run-of-the-mill imaginary figure 8 sort of shapes. And you're basically going to have two unhybridized p orbitals. And again, they're going to do, as I mentioned earlier, what is referred to as sideways overlap. So again, remember when you kind of look at a p orbital, sort of, there's a part here which is referred to as the node, where there's really no amplitude. And the probability, remember that, you know, all these orbitals are really just sort of probability maps, right? So sort of high probability, low probability areas where you could perhaps find an electron hanging out. We don't really know where it is or how it's moving or anything like that. But the highest probability in sort of a p orbital, right, is sort of in this region where there's some amplitude and of finding an electron. That's why we see this sort of overlapping happening within those regions of a p orbital, because that's a pretty high probability of where an electron probably is going to be. Don't really know in the case of our, remember that, you know, when we get this unhybridized p orbital, it has one electron in there. You know, maybe the electron's over here, or maybe the electron's over here. So we get this kind of overlapping happening in both regions to really make sure that we kind of get those electrons overlapping with each other as they come together. And we get this sideways overlap, which again results in our pi bond that's forming. You can kind of think of right about here in the center, sort of the axis of where the sigma bond is happening. So you got kind of like this sigma bond sort of happening, you know, across the middle here. And then you got this pi bond above and below it that's going to represent sort of the double bond that's sort of happening in that situation. And then we have our triple bond, which obviously, as we were to draw it on a Lewis structure or something like that, would basically be 3 lines. And again, we have a sigma bond that's occurring, we have a pi bond, and we have another pi bond. And as I very badly tried to draw it earlier, we basically have 2 of these situations occurring. So remember the px, py, and pz, they're sort of in different orientations in 3-dimensional space. So you have a set of, say, py orbitals overlapping, and you have another set, you know, sort of at a different angle, if you will, doing an overlapping along with your original guys overlapping as well. And I'm not an artist, which is obviously why I don't teach art. But we got sort of these double set of unhybridized p orbitals doing kind of like a pi bond and another pi bond, along with, again, our, if you want to think about it, sigma bond sort of happening in the middle. And again, that's what basically makes up a triple bond when we see it. Any questions on that there? So let's sort of see this in sort of action, if you will. We're going to kind of dissect an organic sort of molecule that has, say, a double bond and stuff like that. And again, I'm gonna draw it with the arrows and stuff like that. You don't necessarily have to draw the arrows or know how to draw the arrows per se. It's just to try to help you understand sort of where the electrons are sort of ending up, you know, where these bonds sort of happening. So I will not ask you to draw the arrows and stuff like that, you know, for this. But again, I'm just going to show it to you. So hopefully you could kind of keep track of sort of where all the electrons sort of ended up in terms of the bonds, and that hopefully will give you a better understanding of what's happening. So again, the arrows are there to hopefully help you get a better understanding of what's happening. You won't necessarily obviously have to draw the arrows. You just have to obviously give the hybridization and so forth. All right. That little warning out of the way there. Let's take a look at like an organic guy, which is known as Ethyne. And it basically contains a double bond between 2 carbons. And it's got a hydrogen, and it's got a hydrogen, and it's got a hydrogen, and it's got a hydrogen. So we've got a bunch of different bonds sort of happening. We actually have 2 central atoms in this case. So as we talked about with sort of the geometry and everything like that, that's not an issue. We definitely can do geometry for each of the central atoms separately. We could apply hybridization to each of these guys. So what I'm going to do is number the carbons. I'm going to call this guy on the left carbon number 1, and this guy on the right basically carbon number 2. And the first thing that we're going to do is, by the way, we'll just do the geometry of both of them. If we were going to do the geometry as we talked about before, we basically would kind of put our hand over on the right-hand side and look at just carbon number 1. And if we look at carbon number 1, it has 3 electron pairs. So carbon number 1 basically has 3 electron pairs. And again, I'll highlight it for you. If we were putting our hand over the right-hand side, 1 electron pair, 2 electron pairs, but we would still count this as an electron pair. Remember, it's a double bond, so we still count it as just 1 bond, just like we did with geometry. So it would have 3 electron pairs. It also would have 1, 2, 3 bonds, right? So a couple of things that we could kind of get off in terms of carbon number 1, just from doing that, is we know that the electron pair geometry is trigonal planar. And the molecular geometry here would also be trigonal planar, right? There are no dots around the center atom, so they have the exact same name. More importantly, though, in terms of hybridization, the thing that will help us in terms of hybridization is really the electron pair geometry and really how many electron pairs there are. There are 3 electron pairs. And again, that is 1, 2, and 3 happening there. 3 electron pairs tells us that if we were to be asked what is the hybridization of the carbon on the left, we could again make our little kind of sheet here and go 1, 2, and 3. That's an S and 2 P's, which means the hybridization of carbon number 1 should be sp2 hybridized. First off, any questions on how I got the geometry or how I got the hybridization there of that guy? We then would essentially do the exact same thing for carbon number 2 here, which I don't want to ruin it for you, but will end up actually the same in this particular case. Not always the case, but if we look at it, we would count our electron pairs. And for carbon number 2, we would now kind of put our hand over carbon number 1 and go 1 electron pair, 2 electron pairs, and 3 electron pairs going that way. So it does have 3 electron pairs, just like carbon number 1. It also has 3 bonds, just like carbon number 1. Again, 1, 2, and 3, the yellow guys are also our bonds, treating our double bond in the middle there, again, as a single electron pair and a single bond, which means for carbon number 2, if we were asked what is the electron pair geometry, it would also be trigonal planar. And the molecular geometry would also be trigonal planar. And again, it is our electron pairs that are important for our hybridization, also going to be 3, 1, 2, 3, which means that the hybridization of carbon number 2 here, we can get over there to right, is also going to be sp2. So just from what we've been talking about, and by drawing a correct Lewis structure here, we're able to identify the hybridization of both central atoms, which in this case, they happen to be the same, sp2 in each case. We're also able to identify the electron pair geometry for both carbons, which happens to be the same, not always the case, and also the molecular geometry here. And again, this is a situation where obviously we have 2 central atoms in this case. Any questions on any of that so far? Now, as I talked about before, hydrogens is pretty much the other element that we see here. We would not really apply hybridization to hydrogen because it only has 1 electron. So it really will not go through hybridization. So really when we're dealing with hydrogen really, if we want to kind of figure out, what are we dealing with in terms of the orbital that's involved with hydrogen, if we just write the electron configuration, it's 1s1, which means each of those hydrogens are basically dealing with a 1s orbital. That's basically the orbital that's involved there with each of the hydrogens that are present. Each of the carbons that are present, if we apply hybridization to it, are dealing with sp2 hybridization. Any questions on that so far? Okay, so now that we sort of understand, what the hybridization is of everybody, sort of what orbitals are there, we're now going to try to use, again, those kind of arrows and boxes to understand where all of the bonds sort of come from within this sort of molecule. So the first thing that we're going to do is, I'm going to draw a line, I think, across. First thing we're going to kind of deal with is really, we have two central atoms. So we're going to be dealing with both carbons. And carbon in general, right, in terms of its electron configuration, as we talked about previously, is 6, which would be our 1s2, 2s2, 2p4. It has our 2, 4 carbon. That is way too many electrons. I probably should count. Try that again. All right. All right, math wasn't my thing either. All right, so 1s2, 2s2, 2p2 would be much better. That seems more like 6. And that gives us our 4 valence electrons, right? So if we were just to look at the carbon and sort of where it started with, and we drew our sort of arrows, we would have our 2p, which has an electron there, an electron there. We have our 2s, which has a couple of electrons. Again, this is carbon. And basically, we would get our promotion of our electron up there, and that would get us very badly drawn boxes. We get us something like this. And remember, though, that the importance here is we've identified that this carbon is actually going to go through sp2 hybridization, which means when it goes through hybridization, it's going to take an s orbital and 2 p orbitals, which means it's going to take this s orbital, 1 p orbital, and 2 p orbitals. So these 3 here are really the ones that are going to go through hybridization. And what that's going to result in is we took 3 atomic orbitals there. That's going to result in 3 sp2 hybrid orbitals, which each contain an electron, as you can see. And we also have this is actually the pz orbital that is unhybridized. Any questions on that so far? And again, this is all about the carbon 1, and also carbon 2 in this case. So when it goes through hybridization, what we end up with on both carbons is essentially these guys. We basically end up with this situation happening on both carbons, right? They both are going to do sp2 hybridization. All right. So they're both going to end up the same sort of situation. So again, I'll draw a little line here. All right, move a couple of things out of my way. There you go. So what I'm going to do now is just draw really my hybrid orbitals, right? So in my hybrid orbitals, in this case, I have my 3 sp2 hybrid orbitals, which again, each have 1 electron involved. I have my 1 unhybridized p orbital, which is really the pz orbital, unhybridized. And this would be for carbon number 1, okay? This guy on the left. Carbon number 2, which is identical in terms of hybridization and everything, will end up the exact same way. It will have 3 sp2 hybrid orbitals that each have an electron in it. It will also have its pz orbital that's unhybridized. and this would be carbon number 2. All right, everybody with me so far? All right, so again, I'm just going to try to, and again, not correct the way I'm going to kind of connect all these guys, but just to visually give you an idea of where all of these bonds are going to come from. So I'll redraw our molecule over here so it's easier to see. We got C1 double bonded to C2, and we got an H, and we got an H, and we got an H, and we got an H. All right, so basically what that means is, as we talked about a second ago, we basically have, in addition to our 2 carbons there, we also have 4 hydrogens that are present, right? Basically 1, 2, 3, and 4. Each of those hydrogens has 1 electron in its 1s orbital. So I'm just going to kind of draw it over here, not correct in terms of energy, but we have a hydrogen that's hanging out that has a 1s orbital and an electron. We have another hydrogen that's hanging out that has a 1s orbital and an electron. We also have a couple of hydrogens on the left-hand side as well hanging out. Okay. So again, here, this is just to sort of illustrate to you sort of where all of our bonds are going to kind of come from and where everything sort of ends up. So let's take a look at, start making some of these bonds and see if we could account for all the electrons that we see. We're going to call this bond, just randomly picking bond number 1. We'll call this bond here between the carbon hydrogen bond number 2. We'll call this guy bond number 3. And we'll call this guy bond number 4 between the carbon and hydrogen. So the first thing that we basically have is a bond between carbon number 1 and a hydrogen. And that would be represented, for example, by these 2 guys coming together and obviously sharing those electrons, right, to make that bond. And that would be bond number 1. And that would be a bond between a 1s orbital of hydrogen and an sp2 orbital of carbon number 1. We also have a similar bond for bond number 2, which is between carbon and hydrogen, which would be, say, this electron coming over here and sharing with this guy and making bond number 2 here. Again, between a 1s orbital in hydrogen and an sp2 orbital there in our carbon number 1. We have almost identical bonds happening over there on the right-hand side between carbon number 2 and hydrogen. So for example, carbon number 2 and hydrogen over there makes a bond which would represent bond number 3, a bond between the sp2 hybrid orbital in carbon number 2 and the 1s orbital in the hydrogen. We also have bond number 4, which would be these guys coming together, for example, making the bond between the sp2 hybrid orbital and the 1s orbital in hydrogen. First off, any questions so far on where everybody's going? So by doing these arrows, again, we have now accounted for really 4 bonds that we see in this guy. We've accounted for this bond, we've accounted for this bond, we've accounted for this bond, and this bond represented obviously here, 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 and here. In terms of how many electrons are left in the carbon, right? In terms of the carbon, there's basically 2 electrons in carbon number 1 left over and 2 electrons in carbon number 2 that are left over. So now that brings us to what is left in terms of the bonds that we have to deal with. And what's left in terms of the bonds we have to deal with are these guys right here. Is the double bond between the carbon and the carbon. Now, if you remember, we talked about the idea that a double bond is really, if we just blow up that bond, double bond, is really a sigma bond and a pi bond. So where do we get those guys from? Well, what's going to happen is we have an electron in the sp2 orbital of carbon number 1 and an electron in the sp2 orbital of carbon number 2, which are able to come together head to head and make that sigma bond. So that's going to make that sigma bond between those two electrons. And again, you could think about it as sort of the first bond that you would draw for the double bond. It would represent this guy here, right? It would be like this. So now we're almost done. We're almost out of bonds. The last bond that we have is actually between carbon and carbon, but it's going to be the pi bond. So if you remember, the pi bond is not head-to-head overlap, but sideways overlap that's going to happen, in this case, from carbon number 1's pz orbital, which was unhybridized, and carbon number 2's pz orbital that was also unhybridized. Going to do is sideways overlap to make that pi bond. And if we do that, the pi bond would come from these unhybridized orbitals doing the sideways overlap and making that sort of second line, if you will, and that pi bond that's going to happen in this case. And again, we'll just use maybe that color there, representing the pi bond that happens there. So here we see that hybridization can actually account for every single electron and basically where they end up. They end up with a double bond in the middle consisting of a sigma bond, which really consists of, you could even get super specific if you're asked. You could say that this sigma bond's between an sp2 hybrid orbital and another sp2 hybrid orbital within the two carbons. You could say the pi bond is really between pz and a pz unhybridized orbital. You could say, as we talked about earlier, that these carbon hydrogen bonds are between sp2 and a 1s orbital. So you get really specific about, what orbitals are involved and which orbitals you would expect to be involved in terms of the bonding that's occurring. First off, any questions on sort of where all the electrons went to and how the double bond sort of comes about? And again, you would not be asked to draw the arrows. They're just hopefully supposed to give you a visual representation of sort of where everybody's ending up. Now, let's tie this to, again, sort of what we were talking about as well in terms of sigma and pi bonds. In this overall molecule, how many total sigma bonds would there be? And the answer would be every single bond that is like a single bond would be a sigma bond, which means number 3 here would be a sigma bond. Number 4 would be a sigma bond. Number 2 would be a sigma bond. Number 1 would be a sigma bond. So within this particular molecule, there is 1, 2, 3, 4, and the one people miss often is the 5th sigma bond that is hiding within the double bond region, and it has only 1 pi bond in the entire molecule. Any questions on how I got those numbers there? So again, you can see hybridization does account for our double bonds, sort of what's happening and stuff with that. Now let's take a look sort of again, what is happening when we're dealing with, say, a triple bond, and where sort of the, if you will, third line came from when we deal with a triple bond. So let's take a look at one of those just to, again, illustrate this. So let's take a look at kind of the same setup. We're going to do a carbon with a triple bond to another carbon that has a hydrogen at the end. This is what's known as ethyne. We'll do the same thing. We'll call the guy on the left carbon number 1, guy on the right carbon number 2. And again, question? So if we do the same thing with carbon number 1, remember that we'll essentially put our hand over the right-hand side there where the carbon number 2 is at. And we would count up electron pairs, and that's going to give us a number of things that's important to us. Remember, we got 1 electron pair here. The triple bond counts as only one electron pair. So basically this guy on the left there for carbon number 1 has 2 electron pairs. It also then has 2 bonds as well. So it's got 2 electron pairs and it's got 2 bonds. And that gives us an electron pair geometry of linear. Also gives us a molecular geometry of linear as well. And if we were to do the hybridization here for carbon number 1, again, we could do our S, our P, and our D, 1 and 2 electron pairs, which means that this guy here is going to hybridize as SP. If we do carbon number 2, it will actually end up the same. It has 1 electron pair on the right, 2 electron pairs on the left, also has 2 bonds, has linear and linear, also going to end up as SP hybridization. Any questions on that there? Okay, so again, kind of like what we did before, we're going to just look at the carbon, and we got 2 carbons. In this case, did hybridize the same. Not always going to hybridize the same, but it did in this case. So if we look at carbon, it's got our same electron configuration as we did on the previous page. I'll try to write it correctly this time. 1s2, 2s2, 2p2. It's got our same 4 valence electrons, which again, if we kind of draw unhybridized, we got our 1, 2, 3, and 4. In this particular case, we're going to get this electron to come up to here, going to give us an electron pretty much in everybody. But different than last time is we would expect this guy to hybridize based on the electron pairs, not as sp2, but it's going to hybridize as only sp. And what does that mean? It means what we talked about. We're basically going to take an s and just one of these p orbitals. And because we hybridize 2 atomic orbitals in this case, we would expect to end up with 2 sp orbitals that each have an electron. Now, different than what happened in the previous example, we actually now have 2 orbitals here, 2 p orbitals that did not hybridize. So we end up with like a py and a pz orbital that are unhybridized that also has 2 electrons, 1 in each of those things. So again, we get a little bit different of a hybridization occurring here, different orbitals involved because of the type of hybridization that's occurring. And in this particular case, what we see is we end up with sp hybrid orbitals, 2 of them. And because both of these carbons are the same, we're going to end up with the same hybridization occurring on both carbons. So I'm going to now draw my arrows so we can follow where everybody comes to in terms of where all the electrons end up. All right, so on one side we have carbon number 1 that has sp hybridized, which again means it's got 2 sp orbitals, each with an electron. Also has our nicely unhybridized p orbitals, or py or pz orbital that also has an electron in each of them. We have basically a matching set on the other side for carbon number 2. Also sp, also got an electron happening there. Also has py, pz orbitals that are unhybridized. So again, here we have our 2 carbons that basically have formed 2 hybrid orbitals, also 2 unhybridized p orbitals. And in this case, we actually have 2 hydrogens. These are going to be the same. Remember, hydrogen will not hybridize, so we'll have a 1s orbital for the hydrogen hanging out. And again, not drawn correctly in terms of energy, but just for space and purposes here. And that takes care of everybody that's involved, right? 2 carbons, 2 hydrogens. Those are all of our electrons that are basically involved in this particular molecule. And I'm going to redraw it over here. Maybe really big. 1, 2, 3, and this. All right, so let us identify sort of where all of our bonds basically come from. So we'll just randomly sort of number these bonds in a sort of random order here, but we'll just call this guy number 1 and this guy number 2. So hopefully you can clearly see that number 1 is going to be between an sp hybrid orbital in carbon and a 1s orbital there in the hydrogen. Those guys are going to come together and overlap. We also will get a similar bond happening between carbon number 2 and the 1s orbital and hydrogen happening over there. So that accounts for the 2 bonds that we see between carbon and hydrogen. Again, each of those guys supplying 1 electron, right? And that's the idea, is sharing electron, right? They're kind of both supplying the electron there that's going to be shared as they come together and basically overlap. By the way, these guys will come together basically head on, because you could kind of, again, simplify and go one line like a single bond. This would be a sigma bond that would happen between those guys. And this would be a sigma bond that would happen. Again, what that just means is the 1s orbital, which is kind of like a circle, the sp orbital, which is kind of like a kidney bean, kind of will come together and basically hit each other and come straight at each other on the same sort of axis in the same orientation, and have that area of overlapping that's going to basically occur. Now, when we look at our triple bond, remember that our triple bond is basically made up of 3 things. The first sort of line, if you want to think about it, is going to be a sigma bond. The next one will be a pi bond, and the next one would be a pi bond. So we could account for where all of those sort of bonds come from and those electrons come from by looking back at our little diagram here. And we see that we have an electron in the carbon number 1 that's going to go and bond with the electron in carbon number 2. They're going to come straight at each other and do a sigma bond, and that would be between an sp orbital in carbon number 1 and an sp orbital in carbon number 2, basically coming together to make that bond. So that takes care of our sort of first bond there in our triple bond. And we highlight it, that takes care of this bond right here. So now we have our first pi bond that would occur, and our first pi bond that would occur, maybe this guy here, will come from these unhybridized p orbitals. So again, these unhybridized p orbitals are going to do that sideways overlap, and perhaps our next guy comes from the bonding of these 2 p orbitals that are unhybridized, and this would result in our pi bond. Again, a result of that is we have our p orbitals again doing that sideways overlap that's happening there. And that leaves us one last bond to go, which is our third bond in our triple bond, and our second pi bond that's going to occur. And again, we'll just grab something to highlight with. We'll go with that color, maybe. We'll go with this. And that's going to perhaps result from these 2 guys coming together here to make that triple bond that's going to occur. Also going to be a pi bond, and that would account for our triple bond. And again, really what that means, I'll give it the old college try, one more bad drawing here. Again, we have kind of a overlapping happening of a second p orbital, making that sort of triple bond, again with the sigma bond sort of in the middle there. And again, here we see that we can account for every single bond that we see in this particular molecule. We can see what electrons are coming together to make our double bond, triple bond, and so forth. The reason we can make the triple bond is because this guy will hybridize as sp rather than sp2, because with the sp2 hybridization, like the previous example, it only left us in the previous example really one unhybridized, whoops, where'd it go? It only left us one unhybridized p orbital, right? Which means we were only able to make that double bond. But because this guy decided to hybridize as sp, it gives us the availability of that extra unhybridized p orbital, which allows the electrons to come together in that sideways fashion and basically make that triple bond occur. Any questions on that there? Now, again, if we were asked a question, how many total sigma bonds are there in this particular molecule? Total number of sigma bonds would be 3 sigma bonds. Again, this would be number 1, this would be 2, and this would be 3. Total number of pi bonds would be 2 in this case, basically making up the rest of our triple bond happening from here. So this guy would have a total of 3 sigma bonds and 2 pi bonds. Any questions on that one there? So again, you won't be asked to draw the arrows. It's just hopefully to give you a visual representation of where everybody's coming from. But you do need to be able to identify the hybridization of any atom. We've applied hybridization here to the central atoms. You can apply hybridization to outside atoms. It's sometimes done as well. So you could apply it to outside atoms as well, the same way. Count up electron pairs and stuff like that. Again, typically the only thing that we don't apply hybridization to is hydrogen. But you can apply it to, sometimes the outside atoms as well. So why don't you take a look at one and answer maybe a question that you might need to know how to do, or you should know how to answer, hopefully. So let me just draw a really crazy structure here. Maybe I don't know how crazy it is, but let me see. What do I want to draw? Let's draw let's do draw one with a bunch of center atoms to see what we come up with. Okay, so we'll call this guy carbon number 1, this one carbon number 2, carbon number 3, carbon number 4. What I want you to determine is what is the hybridization for carbon number 1, carbon number 2, carbon number 3, carbon number 4. Let's do the oxygen, why not, on the outside. Let's do the hybridization for all those guys. Let's also figure out the total number of sigma bonds that are present and total number of pi bonds present. Let's also do for carbon number 1, carbon number 2, carbon number 3, and carbon number 4. What is the electron pair geometry for each of them? And the molecular geometry. All right, so take a few minutes and dissect this guy. Again, you don't have to draw any of the arrows or anything like that. You actually don't even need to draw the arrows to figure all these answers out. So think about what you come up with, and we'll talk about it here in just a second. Maybe right. There we go. All right, so what I'm going to do, I think I'm just going to make kind of like a little table maybe. So what we got there. So if you look at the first one, we got carbon 1, we got carbon 2, carbon 3, we got carbon 4, and we also have oxygen, I guess we'll put in there. So we're looking for a couple of things. We're looking for, just to help us along, number of electron pairs will be helpful. Number of bonds. I'll draw that down there. That will give us the electron geometry name, right? It'll also give us a molecular geometry name. As I make it super small and hard to write in a second. And also our hybridization. That should take care of most of everything I think we're looking for. All right, so let's see what we end up with here. And again, we'll fill in our table. That should maybe help us along the way. All right, so let's see what we got. We'll start with carbon number 1. So really, when you're doing geometry or any of those things, really the first thing you want to do is figure out how many electron pairs and how many bonds. That's sort of the best sort of approach. So we got multiple central atoms. So the idea here is we're really just going to put our hand over pretty much from carbon number 2 all the way over to carbon number 4. We're just going to look at carbon number 1. We are going to count the bond that is, where we're kind of putting our hand over virtually here. So this has 1 electron pair, 2 electron pairs. And again, we do need to count, that electron pair there going to that other side. It is a double bond, but it will only count as 1, which means it has 3 electron pairs. It also then has 1, 2, 3 bonds happening. Now, with 3 electron pairs, that tells us that the electron pair geometry is going to be trigonal planar. Squeeze it in. Also going to tell us with 3 electron pairs and 3 bonds, it's going to have the same name for our molecular geometry. Again, there's no dots. So all bonding electrons means electron pair geometry, and molecular geometry will be the same in this particular case. Again, double bond and triple bond counts as only 1 electron pair and 1 bond. Now we get to hybridization, which again, we could use our little sort of method here to assign hybridization to this guy. And it is based on electron pairs. And electron pairs, there's 3, which means 1, 2, and 3, which means carbon number 1 has the appropriate sp2 hybridization that's occurring there. Any questions on that so far? Now let's go to carbon number 2. And carbon number 2, we're going to do basically the same thing, except that in this case, we're going to put our hand over basically carbon 3 and on, and carbon number 1, which means when we count up electron pairs for carbon number 2, 1 electron pair, 2 electron pairs, we do count that, and 3 electron pairs happening there for carbon number 2. So that gives us 3 electron pairs. Also gives us 3 bonds. Again, double bond on the left there going to count as 1 bond. Going to give us also trigonal planar, or triangular, and trigonal planar for our molecular geometry. Again, no dots here on the central atom, which means both of those names will be the same. Just like previously, it is the electron pairs that are important for hybridization. So if we come up here and count it, 1, 2, 3, that again is an S and 2 Ps, which means the hybridization of this guy would be sp2. Any questions on that one there? Continuing down in my very big drawing, I'm regretting right about now, but my big drawing here coming to the next one, we'll go this way. We're going to put our hand over basically carbon 1 and 2 on the left-hand side. We're going to put our hand over carbon number 4 on the right-hand side, but we're still going to count those electron pairs. So that's 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. That also means that we have 4 bonds happening there. So 4 electron pairs and 4 bonds. Something with 4 electron pairs is tetrahedral. Also no dots, which means that guy there will also share 4 bonds and 4 electron pairs. We'll share our tetrahedral, that's badly written, tetrahedral molecular geometry as well. Now looking at electron pairs for our hybridization, we end up with 1, 2, 3, and now 4 electron pairs, which means the hybridization of that guy is sp3. Any questions on that there. That then brings us to carbon number 4. And carbon number 4, again, pretty much going to put our hand over carbon 3, 2, and 1. Going to count 1 electron pair there. We will still count the electron pair going into those guys. And now we have a double bond, which again only counts as 1 electron pair. So that means in this particular case, we have actually 3 electron pairs around carbon number 4. In terms of bonds, 1 bond, 2 bond, again, the double bond counts as only 1 bond, which is 3 electron pairs, and 3 bonds means that 3 electron pairs, much like the first few, are going to be trigonal planar in terms of its electron geometry. Again, no dots around the central atom here, which means it is going to be trigonal planar for its molecular geometry as well, and back to only 3 electron pairs, which in terms of the hybridization would put us back to what we had for 3, which was 1, 2, and 3, and same as above, which would be sp3. So this guy at the end would have a sp3 hybridization. Any questions on how I got to any of those things? Now, when we look at oxygen, really oxygen isn't a central atom. It's not really attached to things on both sides. So we wouldn't really do electron geometry or molecular geometry with it. But for the oxygen, we could do hybridization for it. And for hybridization, all we really need to know for the oxygen is how many electron pairs there are. So we would approach it the same way, even though oxygen really isn't a central atom here. We would go to oxygen and go, that is 1 electron pair, 2 electron pairs, and 3 electron pairs. And that's really all that we would need to apply hybridization to the oxygen, which would show us that the oxygen would go 1, 2, 3, would also be hybridized as sp2 in terms of its hybridization. Again, here, none of the hydrogens will go through hybridization because it only has 1 electron, but it would be sp2. Yeah. So carbon number 4, you said. Yeah, carbon number 4 is sp3 because I wrote it wrong. It's actually sp2. Thank you. Carbon number 4 is sp2. I apparently wrote it wrong there. I think I might have said it right, but I think I might have wrote it wrong. It is sp2. Sorry about that. Just to go back over carbon number 4 there, it is 1 electron pair, 2 electron pairs, and 3 electron pairs, which obviously would give us 1, 2, and 3. sp2, I think I might have just kind of wrote it wrong there. So sorry about that. So yeah, it should definitely be sp2. Thank you. And it should match obviously the 3 electron pairs that we see for the oxygen there, and obviously the 3 electron pairs we saw for carbon 1 and carbon 2. So yeah, so sorry about that. So correct that on your notes there. That guy should be sp3. Or so I did again, sp2 should be in that case. All right, so that is, let's see, in terms of answers, that is this answer, that is this answer, this answer. So what we're left with in terms of this first guy is to figure out the total number of sigma bonds there are and pi bonds there are. So let us sort of dissect how we can sort of easily go through this. And how am I going to easily go through this? I'm going to easily redraw it real quick so we can see it unscribbled on, I guess. Let's go this way, that way, and that way, and this way here. Okay, so if we just redraw it so we can kind of see clarity here. No, so the question is the electron pair geometry always going to be the same as the molecular geometry? And the answer is no. It will always be the same. It's the same in this case, in both of these cases. It happens to be, I think, for all of them here. For all of them, they're the same because when you look at the central atom in each of these, there's only bonding electrons, so there's no dots. So whenever you have basically a Lewis structure where you have no dots on the central atom, both of those names will always be the same because they're all bonding electrons. So they behave the same in terms of the geometry. It's only when you start to have dots around any of the central atoms, which are basically non-bonding electrons, that these names will be different. So always going to be the same when there's kind of no dots or non-bonding electrons there. Will be different when there are dots present. Other questions on that? Okay, so I just redrew it, hopefully correct here, right? We got 1, 2, 3, 4 thing. So basically we want to figure out how many sigma bonds there are. So remember that basically every single bond that you kind of lay up here in your picture is really a sigma bond. So there's a sigma bond, that would be a sigma bond. That's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7, that's 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Now, also remember that a double bond is made up of a sigma bond and a pi bond, which means hidden inside this double bond is a sigma bond, and hidden inside this double bond is also a sigma bond. So now that gives me, is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There would be 10 sigma bonds total in this guy, in that case. Now our pi bonds, right, come from that sideways overlap that we talked about in terms of the unhybridized p orbitals. And we see pi bonds occur in double bonds and triple bonds. So in this case, we only have double bonds, which means the second line for our double bond would be a pi bond. And the second line over here would be a pi bond. And that means that we would have a grand total of 2 in this case. Any questions on that? I think we hit all the answers for that first one there. Okay, so then let's go through this one I added there and see how we did on that one and make sure. All right, so this one, a little less guys there, which is good. What did I have there? No, triple bond. Triple bond nitrogen. Okay. So really here we'll look at the carbon in terms of number of electron pairs and number of bonds. And again, we'll do the same thing. We'll kind of put our hand, don't necessarily have to, I guess you can put your hand over to nitrogen, I suppose, but you can put your hand over to nitrogen and you got 1 electron pair on the left for the hydrogen, and that triple bond counts as only 1 electron pair, which means it has 2 electron pairs. And again, that is 1 here, and all that counts as 2, basically total. Also, there's no dots on the central atom, which means it has basically 2 bonds. So in terms of electron geometry, it has basically 2 electron pairs, which is linear. The molecular geometry here would also be linear as well. Again, no dots on the central atom. And in this case, the hybridization of the carbon, if we just kind of follow it here, that is 2 electron pairs, 1 and 2. I'm going to try not to screw this one up this time. Is going to be sp hybridized here, this particular carbon. Any questions on any of that one there? Now, nitrogen, we really aren't going to apply electron geometry or molecular geometry because it's really not a central atom. There's kind of nothing to the right of it, so it's just kind of hanging out there. But we'll apply our hybridization to it. And if we apply hybridization to it, we really want to know electron pairs in this case. And it has 1 electron pair there. And again, on this side, all that's going to count as basically 2 electron pairs. And again, 2 electron pairs would tell us that this guy is sp hybridized as well. So again, we would have basically a linear shape. If you were to build this, this would be straight linear all the way across. in this particular case. Just to, for example, you know, and before we do that, let's just finish up sigma bonds. In terms of sigma bonds, there would be 2. In terms of pi bonds, there would also be 2. And again, just to highlight those for you, our sigma bonds in this particular case, we would have 1 here. And again, kind of the first line there in our triple bond, and our pi bonds would be the remaining 2 lines here and here, basically, would be our pi bonds. Any questions on that one there? No, I just want to kind of to answer a certain earlier question about the molecular geometry, electron pair geometry. Let's just focus in on this oxygen here. And if we were to focus in on this oxygen, we would look at it, and again, we would count electron pairs here. And it would have a grand total of 1, 2, 3, and we would count this guy over here as 4 electron pairs. But in terms of bonds, in this situation, it actually only has 2 bonds that are happening. 1 bond and 2 bonds, basically. And that means that it has 2 bonds. So in terms of the electron pair geometry for this guy, it would be tetrahedral, as that goes with 4 electron pairs. But again, because of the non-bonding electrons and because there's only 2 bonds in this particular case, the molecular geometry of the oxygen in this situation would be bent or V-shaped, kind of like water, basically, is basically what you would have here. So again, because there's dots here around the central atom, we get different names that occur. And that's basically because, as we talked about, that allows the molecule to really kind of flex a little bit more because it's missing that extra bond. It gives our bit a little bit more room to kind of spread out, and it affects the overall geometry of the name. Now, if we wanted the hybridization of this oxygen, the hybridization of this oxygen would be based off of the 4 electron pairs, which would give me 1, 2, 3, and 4, which means the hybridization here would be sp3 in this case. Any questions on that? Okay, questions on obviously all of this. So really, you need to be able to draw the Lewis structure. You need to be able to correctly identify the electron pair geometry. You need to be able to identify the molecular geometry. You need to be able to obviously apply hybridization, give the hybridization. You need to be able to figure out how many sigma bonds. Pi bonds are our total. Obviously, we talked about things like formal charge and stuff like that, all that stuff together. Any questions on any of that stuff that we talked about up to this point? Okay, then we're going to finish here talking about, for today, molecular polarity. And we talked a little bit about polarity earlier. And let me find where we are here. Coming back to the notes. We talked about all that. Okay. We talked about molecular polarity earlier on. And remember, there's sort of 2 types of polarity that we're talking about. In chapter 3, we really, when we were doing the sort of difference in electronegativity values and stuff like that, that's really what we're talking about in terms of bond polarity. And bond polarity really means, like I mentioned a couple of times, basically between these 2 guys, regardless of what other bonds may be in the actual compound or molecule, is the bond between these 2 guys kind of polar or non-polar? And the way we typically can sort of figure out bond polarity is using the electronegativity difference, right? Or just the general trend in electronegativity values. when we have a difference in electronegativity values, that is, remember sort of that above 0.4 value, or just in general, if you use a general trend, that tends to give us a polar bond. If we have a difference between 0 and 0.4, that gives us what's considered a nonpolar bond and considered basically equal sharing of the electrons. So, you know, we have something like, I think we saw HF, you know, versus say H2. Here they have the exact same electronegativity values of like 2.1 each. Gives us a difference in electronegativity value of 0, which means this is going to be nonpolar bond. And what that means is, again, the hydrogen on the left, the hydrogen on the right, they're kind of equally sharing those electrons between them. And that means that there really is no side to this bond that's more negative or more positive. And that's different than when we look at this guy, which is like 2.1, and this guy is 4. We take the difference in electronegativity, 4 minus 2.1 gives us 1.9. That is definitely above 0.4, and that results in a polar bond here. And what that means is there is actually a difference in terms of where the electrons are being held within this bond. They are hanging out closer to the fluorine, which is going to create the fluorine being more negative, which is why it gets what is referred to as a partially negative sort of charge to it. It's partially negative while the hydrogen becomes partially positive, because as we talked about, basically they're still sharing the electrons. So there hasn't been a complete transfer of electrons in this case. They're still hanging on, which means we haven't given somebody like a full transfer of electrons, like what happens when we deal with ionic compounds. In ionic compounds, the metal fully gives away its electron to the non-metal, and that creates a positive overall charge for the metal, creating a cation, and a negative overcharge for our negative overall charge for the non-metal, creating an anion, and they gain those kind of full charges like +1 and -1, and that's the attraction that holds it together. Here, because there is still some aspect of sharing that's happening, we don't get those full charges that occur. We get the partially positive charge, partially negative charge, because they're still kind of hanging in there, but they're not basically sharing equally. This also can be represented by an arrow, which is very commonly seen. We sometimes call this a bond dipole arrow or a dipole arrow. And the arrow points to the side that is more negative, and the kind of back part that, again, makes kind of like a plus sign is the sign that's more positive. Now, this also arrow represents what is referred to as a dipole moment. And if we end up with a molecule as a whole, so what we were just talking about really is bond polarity. What we're talking about now for the rest of this really is molecular polarity, which means as a whole, when you take the entire molecule as a whole, is that entire molecule nonpolar, which means we're going to have nice equal sharing of electrons, or when we take the entire molecule with all its bonds that are present as a whole, is there a side that's more negative? Is there a side that's more positive? And that would be a polar molecule. So what we're really talking about here is, again, the entire molecule together. That encompasses all of the bonds that are present, you know, all the atoms that are present. It also will encompass, in certain cases, the geometries of what's present. And we want to take all that into account to determine whether or not, as a whole, everybody included, is the thing going to be polar or non-polar. If we determine that the molecule is going to be polar in that case, it will contain a dipole moment, and it could be represented as the overall molecule as heading in this direction. This side would be more negative, this side would be more positive. If it's determined to be a non-polar molecule, it does not contain a dipole moment, which means you would not draw the arrow. And essentially what that means is, as we've been talking about, that There is really no side of that molecule that is more negative than the other. I guess that way you could kind of say that is it's sort of neutral in that sense. There is no positive side or negative side. And that's different than in a polar molecule as a whole. There is definitely a side that is more positive based on the way the electrons are being shared overall, and a side that is more negative. Now, the one place where sort of bond polarity, where we kind of use the electronegativity values, and molecular polarity sort of cross over and kind of is the same thing, is what we talked about a little bit in chapter 3. And that is when you're dealing with diatomic molecules. So when you're dealing with diatomic molecules, because that molecule pretty much only has one bond, the whole molecule has one bond, which means if that bond is going to be polar, then the molecule will be polar. And if that bond is going to be nonpolar, then the molecule will be nonpolar. So the one and a kind of only place where, they're kind of the same thing is in the diatomic molecule, where we really just have two things. And it's just a result of the fact that when you're dealing with a diatomic molecule, there's only one bond present, which means if the bond is polar, the molecule will be polar. And if the bond is nonpolar, the molecule will be nonpolar. So there are homonuclear diatomic molecules. Homonuclear basically means kind of the same thing as like a homogeneous mixture. Homogeneous, homonuclear basically means that you have a diatomic molecule that basically contains the exact same elements. So that's things like it shows there. As I cross it out there. Come here, get out of my way there. Thank you. We got H2, two H's together. We got O2, two oxygens together. We got our N2, which is two nitrogens together. Our F2 that we saw as well. Now, every one of these guys here that I just drew are all diatomic molecules. They basically contain two total atoms. They're also homonuclear diatomic molecules because they're both the same atoms. These are both two hydrogens, two oxygens, two nitrogens, two fluorines, which means if you took any one of these guys and went to that electronegativity table and did the difference in electronegativity values for each one of them, they're going to equal 0, which tells us it's a nonpolar bond. Right? So for example, if you take 4 minus 4 is 0. If you take 2.1 minus 2.1 is 0. They're all going to give us a nonpolar bond. And because that is the only bond that is present in each of these molecules, so in this entire molecule, there is just this one bond here, which is nonpolar, and this guy is just this bond that's nonpolar, this bond that's nonpolar, and this guy that's nonpolar. Because the one and only bond in there is nonpolar, for each of these guys, they would all be considered nonpolar molecules. Or the molecular polarity here would be nonpolar, because it's pretty simple. It's going to be a nonpolar bond, only bond there. The molecule is going to be nonpolar. What that essentially means in each of these cases, we would expect that the electrons that are being shared between the two are being shared equally, right? And what that basically means is overall as a molecule, when we think about kind of like the two oxygens together, and again, I apologize for my bad artwork here, but we would expect the electrons to basically be shared equally here. Make it a little bit bigger there on that side. There we go. On both sides. And overall, this thing would for most part be considered like a neutral molecule. There is no side that's more positive. There's no side that's more negative. We have like beautiful equal sharing of those electrons, and it's going to create a pretty neutral sort of environment. And that's different. They definitely would not have a dipole moment in this case. There would be no arrows that would be drawn in this case because they're nonpolar. Any questions on that? Now, this does change in a lot of cases when we go to, say, a heteronuclear diatomic molecule. Heteronuclear is like heterogeneous mixture, which means you see different layers. Basically means that we have different elements involved. Still only two atoms, but actually from different elements. So we've seen a couple, for example, like HCl, HF, obviously, we saw on the previous page as well and earlier. But in each of these cases, generally speaking, you will usually end up with a polar bond. So if we just take a look at HCl and HF, Cl is more electronegative than H, and F is more electronegative than Cl. So we would expect that in this particular case, this bond to be more polar. And we would expect the electrons to be heading towards the chlorine in this case and towards the fluorine in this case, creating, for example, that partially negative charge over there, partially positive charge over here. So these guys would contain polar bonds. And again, in the same reason as we did above, this is the only bond present in this molecule, and this is the only bond present in this molecule, which means that because those are the only bonds that are present in this particular molecule, in addition to that bond being polar, this would also then be a polar molecule, which means unlike our nonpolar guys up here, it will have a dipole moment represented by this arrow, again pointing to the more negative side, and the other side, the more positive side of the bond, or the molecule in this case. And we would have, again, if we thought of kind of the HF molecule, we would have sort of a more of the electrons hanging out over here on the fluorine, which is why this side would become more negative, less of the electrons hanging out over here, which is why it becomes more positive, and why when we draw that arrow, it's pointing towards the fluorine there, and this is over the hydrogen part of it. So unlike a nonpolar molecule, when we do say that this molecule as a whole is polar, what we're essentially saying is there is a side to that molecule because of the overall sort of unequal sharing of electrons that are occurring that ends up being more positive, and the other side ends up being more negative. Any questions on that there? Now, diatomic molecules are really easy to determine whether or not the molecule is polar or nonpolar, because as we just talked about, essentially, because there's only one bond, and as you can see as well up on top, it doesn't matter if it's a single bond, double bond, or triple bond. It doesn't make a difference in terms of electronegativity values and things like that. But because there is only really one bond in it, if you're able to determine that that bond is polar, then you can safely say that that molecule as a whole is going to be polar. And in a diatomic molecule, if you can safely assume that that bond that you see is nonpolar, you can safely assume that the molecule is going to be nonpolar. Now, that would be great if it, worked really well for things that are more than two, but it doesn't. So when we get into things that are actually more than two atoms present, we do actually have to look at a couple of different things to determine whether or not something is going to be a polar molecule or a nonpolar molecule. So let's talk about what really you have to look at when you have three or more atoms involved. when you have three or more atoms involved, you have to look at really two things. You first have to look at, are there polar bonds? And if the answer is no, there is no polar bonds, they're all nonpolar in the molecule, then you're pretty much done. The molecule is going to be nonpolar. So if you're able to identify that every single bond that you have in that particular molecule is nonpolar, then obviously it would be nonpolar in that case. Now, if you determine, well, there are some bonds that are nonpolar, but there are some bonds that are polar, and if there's at least one polar bond present in a molecule, you then have to look at a second aspect of that molecule, because just because you have a polar bond present, it does not necessarily mean that you will have a polar molecule when you have three or more atoms that are present. And the second thing that you have to look at is, okay, if there are polar bonds, what is the molecular geometry or the shape of this particular compound? Now, when you're looking at the shape of it, you do need to take into account that when we draw those bond dipoles, and we draw those little arrows over the bonds to indicate the bond polarity when we're using the difference in electronegativity, those guys are what are sort of referred to as vectors. And vectors have direction, they have magnitude. Then I fell asleep in physics, but I woke up long enough to remember that in certain cases, vectors will sort of add to one another. And in other cases, vectors will sort of cancel one another. So what do I mean? Let's take a look at an example like CO2. If we go through the process of drawing CO2, it will end up looking something like this. Right? So if we draw CO2, the first thing that we would want to know is there polar bonds that are present? And the reality is you would not necessarily need that table of electronegativity values like we talked about, because if you look on the periodic table, you will see carbon, nitrogen, and oxygen all in the same period. And what that tells us is oxygen is further to the right than carbon, which means you can make a pretty safe guess, because remember, it's only when you kind of get the diagonal effect, right, that you could technically cancel each other out. We would know that oxygen should be more electronegative than carbon, which means if I were to draw my bond dipoles, it would be going from the carbon to the oxygen in both directions. So by looking at electronegativity values or just the general trend in electronegativity, you will be able to determine whether or not this thing is polar or non-polar. And I'm sorry, has polar bonds or non-polar bonds. And we will know that this guy does have polar bonds. So check, it does have polar bonds. So you may be tempted to go, it has polar bonds, so it would make sense that this guy is going to be a polar molecule. And that is where we're at right now to determine whether or not this thing is going to be a polar molecule. So the other important thing that we have to look at is, what is the molecular geometry of this guy? So to do molecular geometry, we would go to the carbon. It's got one electron pair, two electron pairs, and it also has two bonds. So this guy has two electron pairs, and it has two bonds. Something with two electron pairs and two bonds tells us that the molecular geometry is linear, which basically means that this guy is a straight line. Again, here we're interested in the molecular geometry, not the electron pair geometry, but actually the molecular geometry of the shape. So what does that mean? Well, it means that if you take something that is a straight line, like my pen here, maybe it comes up, there it is. And basically what we have is oxygen pulling this way, but then we have oxygen pulling the other way. And I'm actually pulling my pen really hard on both directions. And you can kind of see, hopefully my pen is pretty much not going anywhere. I'm pulling both ways really, really hard. Pen is pretty much not moving. And what that essentially means is, in this case, these guys are basically canceling each other out. These dipoles are canceling. And that means that CO2, even though it has polar bonds, is actually a nonpolar molecule. So it actually would not be polar. It's going to be nonpolar. And in this case, because they're going equal and opposite, they sort of cancel each other out. It's kind of like sometimes people think about polarity as like tug of war, like you're pulling on a rope, right? And there's like a little flag. And, you know, if somebody pulls more one way than the other, the little flag will move. And that would indicate kind of like a polar molecule. But if people are pulling equal and opposite of each other, is going to be a nonpolar. They're going to cancel each other out. Kind of the same idea. If both people are pushing on a door equal and opposite of each other, door is not going to open, right? And it's going to stay closed. And so it's sort of the same idea here. So this is a very good illustration that although you can have something that has polar bonds in it, because of the geometry of it, it may actually end up being nonpolar and cancel out. Now, if we look at something, say, like water, for example, and if we want to determine whether or not this guy is polar or nonpolar, we would do the same thing. We want to first see, is there polar bonds or nonpolar bonds? And we would know that oxygen is more electronegative than hydrogen, and we would have bond dipoles heading in this direction. So water here has polar bonds just like CO2 does. So again, we do have to think about the geometry here and see whether or not this guy is going to be polar or non-polar overall. And if we look at the oxygen has 4 electron pairs, 2 bonds and 2 non-bonding electron pairs, and 2 bonds that are occurring. Something with 4 electron pairs and 2 bonds is bent or V-shaped. Hence why I drew it in this kind of V-shaped fashion. So what does that mean? Well, it means in this case, if you think about it like this, like you got something like a triangle, you got a guy coming this way, you got a guy coming this way. You kind of pull from the top, right? If you pull something from the top, you could kind of imagine the whole thing kind of moving. And that's actually what's going to happen. We're going to get a net dipole moment in this case for water that's actually going to run this way. Very badly drawn. It's supposed to be a straightish line. So this dipole moment running this way, which tells us that the hydrogen part of water is more positive, oxygen part of water is more negative. Overall, the electrons in this case are hanging out towards the oxygen versus the hydrogen. What does that really mean? Well, if you take these guys, which are these bond dipoles, and you basically put them kind of point to tell, what that means is if you take the one dipole that was drawn this way, and then you take the other dipole that was drawn this way, they actually add to each other heading in this direction. And that is where our dipole moment basically comes from because of the way the geometry is. You kind of see them pass each other and they add to each other in that direction. And that's why we have the overall dipole moment basically happening in that case. So when we're dealing with things that are 3 or more sort of atoms that are present, we have to look at both, is there polar bonds? And again, if the answer is no, there are no polar bonds, then it will be nonpolar. If there are polar bonds, we have to look at the geometry and see whether or not those sort of bond dipoles or those vectors will add to each other or cancel out with one another. So the question becomes, you know, do I want to kind of draw all these things and try to figure out, are these things going to cancel out with each other? Are they not going to cancel out with each other? Or is there sort of an easier way? And the answer is, like anything, there is sort of an easier way sometimes. Not necessarily maybe 100% foolproof, but pretty darn close to being 100% foolproof. There are certain geometries which are referred to as being symmetrical geometries, and there's certain ones that are referred to as being unsymmetrical geometries. So let me just kind of find somewhere to scribble here. Go back. After this, I think it was something that was empty. Perfect. Go that way. Oops. Okay. So there are certain geometries which are really considered symmetrical geometries. And these symmetrical geometries, let me list some of them up here for you. These are things like trigonal planar. And again, we're talking about molecular geometry here. There's a shape. Tetrahedral. Triangular. Bipyramidal. Octahedral. So what do all of these molecular geometries sort of share in common? If you look back on some of these that we've drawn over the days here, what they all really share in common is when you look at the center atom, there are no non-bonding electrons, basically dots. So when you look at the central atom and you draw it, no non-bonding electron, no dots. And if you have that situation and all of the outside atoms are the same element, it is going to be pretty much almost 100% of the time a nonpolar molecule. So for example, if I draw this guy here, carbon with some fluorine, I look at my central atom, I do not see dots. If I want to, I see 4 electron pairs, I see 4 bonds, I see tetrahedral. I see every single guy on the outside is the exact same element. This is going to be a nonpolar molecule. Does it contain polar bonds? And the answer is yes, it does, because carbon is less electronegative than fluorine, which means if we were to say it does contain polar bonds, definitely heading towards the fluorine in this case, right? But because this is tetrahedral, what that means is all 4 of those fluorines are really spaced out equal and opposite of each other, which means that all 4 of those fluorines, if you want to think about it like the rope example, you have 4 people that are spaced out equal and opposite of each other with like a rope that's connected. And if everybody pulls equally, pretty much everything's going to stay in the same spot. It's not going to move. So although this does have polar bonds, this is another example of, because of the geometry here, which is tetrahedral, and the spacing of everybody's going to kind of pull equally, and they're essentially going to cancel each other. This is obviously not drawn correctly in terms of geometry here, or 3-dimensional space, but essentially the fluorine up there on top and the bottom will end up being equal and opposites of each other, like 2 people pulling on a rope, not going to go anywhere. The other 2 fluorines will also end up equal and opposite of each other, kind of pulling equal, and nothing will happen. And again, even though there's polar bonds, these guys will cancel each other out, and this would be a nonpolar molecule. Now, what happens though if we end up with something that does not have dots on the central atom, but all the elements are not the same on the outside? So let's just change this guy just slightly by taking our fluorine, our our fluorine. And let's just swap out one of those fluorines for a hydrogen. So what happens in terms of this guy? Well, we definitely see 4 electron pairs, 4 bonds. We definitely see no dots on the central atom. We still have polar bonds heading to the fluorine. But what about this carbon-hydrogen bond? That carbon-hydrogen bond is a nonpolar bond, right? Difference in electronegativity is 0.4. So what do we have now? Well, you could kind of think about it that you got all 3 of these guys kind of pulling this way, right? And instead of having this guy like we did above kind of pulling back, right? You now have this guy actually kind of going with them a little bit, right? Because carbon is a little bit more electronegative. So you got everybody sort of pulling in that direction away from the hydrogen. And you could kind of visualize if everybody just got on one side of the rope and pulled, the whole thing would move, right? And this guy now goes from a nonpolar molecule where we had all the fluorines to this guy would now become a polar molecule with a net dipole moment heading probably towards our fluorines being more negative and our hydrogen being more positive in this particular case. Any questions on that? Let me just see your question there. Yeah, so for molecular polarity, so the question is for molecular polarity, do you just write kind of polar molecule or non-polar molecule, or do you draw the arrows? And the answer is you actually do both. You can do both. So for example, like the, so I don't mess up this page too much because I want to come back and draw a little bit of something there. But for example, for like the water example that we just looked at, you could draw the individual bond dipoles, which is what these arrows would represent. So these arrows would represent the bond polarity here. As a result of that, as we talked about a second ago, we do end up with an overall dipole moment, which is also sometimes represented by drawing maybe sometimes a bigger arrow, maybe not always a bigger arrow, but kind of an overall arrow here basically represents the same thing. This side's more negative, this side's more positive, and this would be what is referred to as the dipole moment. And so you can draw the arrows for both, or you could simply, if you're asked, is this guy a polar molecule or non-polar molecule, just write polar molecule. So it is actually represented kind of both ways sometimes. Sometimes people will draw this kind of overall summary arrow, if you will, which is the dipole moment to indicate the entire molecule as a whole. There's unequal sharing happening in the case here near the oxygen being more negative and the hydrogen being more positive, in addition to the individual, what are sometimes referred to as bond dipoles, the little guys. So they're kind of the same representation in terms of an arrow. But most of the time, if you're asked if something is a polar molecule or a non-polar molecule, simply just stating it's polar, the molecule, or non-polar molecule is sufficient. If they specifically ask you to include like the dipole moment, then you would want to include that kind of overall arrow, kind of how I badly did it here, this kind of arrow overall, kind of pointing towards the fluorine side here. That would be the way to represent that. Other questions on that? Okay, so as I was stating here, when we have these symmetrical geometries, one way that you can recognize it is when you look at the Lewis structure, no dots. Everybody on the outside is the same atom. Pretty safe bet to write that it's a nonpolar molecule. If you look at your Lewis structure and there are no dots on the center atom, but everybody on the outside is not the same element, almost a safe bet to write is going to be polar. So again, with anything else, it doesn't maybe work 100% of the time, but pretty darn close in this case. So you could almost pretty closely, if you draw your Lewis structure, no dots, everybody is same on the outside, going to be nonpolar. If if you draw your Lewis structure and you have no dots, but everybody is not the same, then it's a pretty safe bet that it's going to be a polar molecule. So what does that leave us? Well, that leaves us in terms of some geometries which are referred to as being unsymmetrical geometries. And again, here we're looking at molecular geometries. And this would be things like trigonal pyramid. This would be things like angular, bent or V-shaped. V-shaped, there we go. Square pyramid, seesaw, or distorted tetrahedral. You know, what all these guys sort of have in common is when you draw the Lewis structure, you will end up with non-bonding electrons on the center atom. So basically dots, right? So when you draw your Lewis structure, you end up with dots on the center atom. And if you do that, if you draw something that has dots on the center atom and all the outside elements are the same, it's a pretty safe bet that you're going to end up with a polar molecule. So let's talk about a couple of the ones that we saw, right? So if we take something like water, literally you could look at the Lewis structure and go, I see dots. I see the same thing on the outside. This is going to be polar molecule. You know, if you look at something like what we had, you know, if you look at, say, something like NH3 that we saw earlier, I see dots on the central atom. I see everything on the outside the same. This is going to be a polar molecule. So this is sort of a quick way that you can determine polarity. And what we're talking about here is molecular polarity by really looking at your Lewis structure. And if you have this unsymmetrical geometry, that means that you will have dots on the center atom and everything on the outside the same, going to be polar. If you have a symmetrical geometry, you will have no dots on the center atom, everything on the outside the same, it will be non-polar. Or if you have no dots on the central atom, everything on the outside is not the same, it will be polar. It really leaves you just a couple of sort of, I want to say exceptions, or a couple of ones that you really do have to sort of think about, you know, a little bit more than just I see dots, I don't see dots sort of thing. And that is linear. So if you have the molecular geometry of linear, it's basically a straight line, right? So like we saw with CO2, you can have polar bonds, but because they're linear and they're going equal and opposite of each other, they will cancel out. So if you have a linear case where you got this happening, or even if you have a linear case where you have polar bonds heading right at each other, this is going to result in a nonpolar molecule like it did with our CO2, this being nonpolar. Again, heading right at each other is like my door example. Two people on opposite sides of the door pushing equally. Door is really not going to move anywhere. They're going to cancel each other out. But it is possible that you could end up in a linear situation where everybody is sort of heading in the same direction, right? And in this case, this would be a polar molecule because it's like everybody kind of just pushing in the same direction. So linear is really the only one you have to sort of think about for the most part. But the good news is because it's linear, just think of it like a straight line. So either if they're going equal and opposite of each other, they're going to cancel. If they're all heading in the same direction, it is going to be a polar molecule. Question on that one there. Now, I know I talked about symmetrical geometries and the idea that you know, pretty much it is when we draw a Lewis structure and there's no dots on the central atom. There are actually two exceptions where you could potentially have a molecular geometry that you draw that actually has dots on the central atom, but still be nonpolar. And the two that really come up is linear, and it's not the linear that we were just talking about, but it's the expanded octet linear. So if you remember the expanded octet linear, and my really bad drawing is something like this. Kind of your, what we got there, 5 electron pairs and 2 bonds. This expanded octet linear. And if you remember, these kind of guys make like that triangle sort of happening. And these guys end up being 180 degrees apart from each other. So that expanded octet linear. If you have this geometry and both of these guys, the x's, are the same, it is going to be nonpolar, because essentially what you have is a straight line. And if you have both of those things the same, they're going to cancel each other out. The non-bonding electrons also sort of cancel each other out as well. So that's sort of an exception to our symmetrical geometries where you actually do see dots, but it will be nonpolar as long as those guys are the same. The other sort of exception where you could draw one where you see dots is our central atom that, you know, has sort of this arrangement here. I guess we'll do this. This is our square planar arrangement. Very bad square there. I think I'm making it worse. There you go. So that's our square planar geometry, also an expanded octet. And again, here we do have dots, but if all these guys on the outside are the same element, it's basically a square, right? And a square basically is 2 people going this way and 2 people going this way. And if they're the same, they will cancel each other out. So those are sort of 2 exceptions that we come across sometimes where we do draw the Lewis structures and we see dots. But because of the geometry here, either being linear or square planar, if everybody on the outside is the same element, it will end up being nonpolar, you know, like our guys up here. So you could kind of add those to our symmetrical geometries, even though they sort of have dots. So that's sort of the, I won't say easiest way, but kind of the quickest way to probably for the most part safely determine whether or not you're dealing with a polar molecule or a nonpolar molecule is to draw the Lewis structure. And again, if you see no dots on the central atom, everything's the same, going to be nonpolar. If you see no dots and everything is not the same, probably going to be polar molecule overall, which would possess a dipole moment. And again, the 2 exceptions there is if you have the expanded linear geometry or the expanded square planar geometry and everything's the same, then it would be nonpolar as well. And that then goes with our unsymmetrical geometries where basically if you draw the Lewis structure and you see dots and everybody's the same on the outside, it's a pretty safe bet that it is going to be polar molecule overall. And again, if it is a polar molecule overall, it means it has a dipole moment. And if it has a dipole moment, it means it has an arrow like this, which represents overall for the entire molecule, where the electrons are being shared unequally, which side is more negative and which side is more positive. Any questions on molecular polarity? Sort of the quick way to determine, in most cases, if it's a polar molecule or a nonpolar molecule. We get back to where we were to look at just a couple of examples with some drawings there. Okay, so we talked about some of this, and again on this slide, Polarity does affect a lot of things about intermolecular forces, which we'll talk about in a later chapter. But the polarity of a molecule basically affects how one molecule can interact with another molecule, how they're able to basically interact with each other, and affect things like boiling points, melting points, freezing points, and also solubility, whether or not these things will mix together. So let's take a look at some examples here. Some of these we talked about. This is our HCl. Again, we can see that it is a diatomic molecule, and because the hydrogen chlorine bond is polar, and that's the only bond that is present in that molecule, we would expect this molecule to be polar overall and have a molecular polarity where both the bond dipole here and the dipole moment are basically the same arrow. Again, this side more negative, this side more positive. And that's what we see here, kind of the reddish color, or more redder color. It kind of looks yellow and orange here, but that implies more electron density happening on the right-hand side, which is what is making it more partially negative on that side of the molecule and more positive on that side. Here's our CO2 that we also saw. Again, a very good example, as we talked about, that it definitely does have polar bonds. And again, these would be our bond dipoles. But because of the geometry here of being linear, even though this guy is pulling to the left, this guy is pulling to the right, and because they are a straight line, they essentially will cancel each other out. And overall, this guy is going to be a nonpolar molecule, which, as you can see, a little bit equal of this sharing of electrons, right? So we have kind of the same electron cloud on both sides, as opposed to what we see here, a much larger sort of electron cloud happening closer to the chlorine. And again, we end up with sort of equal sharing of electrons as a whole. Again, we would not draw any type of dipole moment arrow for this because it's not polar. And basically, again, you could kind of think of it like being neutral. There is no positive side or negative side to that particular case. There's our water example that we did a second ago. And again, with our water, we do see our polar bonds. So these are our bond dipoles heading toward, again, pointing to the more electronegative element, the one more positive, making the plus sign. And this arrow here coming through the center is our net dipole moment. And really what that is kind of like what I did a moment ago. And again, technically speaking, if you take these vectors and you add them, you get sort of, again, that net dipole moment that's sort of happening here. And sometimes it may be a big arrow net, or the dipole moment may be a relatively small arrow as well, depending on how they come together. But what that means is what we see is pointing net dipole moment that near the oxygen side is more negative, hydrogen side more positive. And we see that when we look at this is much more red in this region near the oxygen. Red means a higher density of electrons being present. The side down here by the hydrogens are more blue, blue meaning cold, not as many electrons being found there. So we get this unequal distribution as a whole in terms of how the electrons are being shared, creating this polar molecule, which means one side is more positive, one side is more negative. And again, if we just take it back to our Lewis structure, we see dots on the central atom, everybody on the outside is the same, going to be a polar molecule. And that's exactly what we see here. We talked about NH3 as well. Again, if we just bring it back to our Lewis structure, I see dots, I see everything on the outside the same, going to be a polar molecule. Again, between nitrogen and hydrogen, there are polar bonds, and these are our bond dipoles. Again, these guys are adding based on the geometry. Remember, we have our non-bonding electrons coming this way, kind of like everybody is pushing upwards. And this would represent the net dipole moment that's happening. basically telling us that in this particular case, the nitrogen is more negative in this compound. The hydrogen is actually more positive in this compound, again, because we have that polar bonds sort of heading, you know, and again, we have that. So it makes this sort of trigonal pyramid sort of shape. And those non-bonded electrons, are pulling that way as well. And again, that's sort of our electron pair geometry and our trigonal pyramid sort of shape that's occurring in this particular case. And we would expect it to be a polar molecule. As I mentioned before, and we'll get into more detail on this in sort of a later chapter, but really that kind of polarity of a molecule has a very big effect on whether or not things are soluble in each other. And if things are soluble in each other, what that really means is they're able to mix really well. And they have ways to interact with each other. And as we'll talk about, the basic interaction that occurs when we're dealing with sort of molecules interacting with each other through intermolecular forces is the basic attraction between positive and negative, that basic kind of positive negative attraction, which means when you get two polar molecules together, this polar molecule has a side that's more positive, this side is more negative. This polar molecule also has a side that's more positive and negative. And that gives these two polar molecules a really good way to interact with each other. But if you take something that is nonpolar, which basically has no charge, and something that is polar, which basically has an overall kind of fixed charge, they have no real good way to interact with each other over the long period of time. And that's what we see here with oil. Oil is pretty much nonpolar, which means it's kind of neutral. Water is polar, as we saw. Over a long period of time, these two guys pretty much have no way to maintain an interaction with each other. We'll talk about a way they can a little bit later on in a different chapter, but over the long period of time, they really don't have that kind of positive, negative way of interacting really well with one another. And the result of that is that they pretty much won't mix. They're not going to be soluble in each other. They're basically going to kind of separate out, which is what we see here. That's basically soap, and soap basically contains, as we'll talk about in a later chapter as well, a part that is nonpolar and a part that is polar. So you definitely can have a molecule that has a polar part to it and a nonpolar part. And that works really well for soap, as we'll talk about, because basically dirt is nonpolar. So nonpolar and nonpolar side of soap work really well. Dirt, which is nonpolar, and the nonpolar side of soap will mix together. Because when you take something that's nonpolar and interact it with something that's nonpolar, they actually can sort of interact with each other really well because they are using the similar type of forces. And then the polar part works really well because usually when we use soap, we put water, which is polar, to wash it off. So when we wash off our soap, the soap basically traps the dirt that's dirty and non-polar, and it all goes out and you are clean. And we'll get more into how to do soap, obviously, how soap works in a later chapter. But let's just finish up here, as we've been talking a while here about our kind of polar molecules and non-polar molecules and how we could determine it. So why don't you take a second here and decide for each of these, is this going to be a polar molecule or a non-polar molecule, and see what you come up with. And while we're at it, I'll add a couple more here just to kind of finish it up. Let's do a couple that we saw earlier, I think. Okay, so for each of these, decide whether or not it is a polar or non-polar molecule. And we'll do one more here. Okay, take a couple minutes and we'll finish it up here. Look at this, and again, for the most part, even though they sort of give us some electronegativity values and stuff like that, for the most part, you don't necessarily need them in most cases, but we'll use it here on the first one, and then we'll kind of go through the other ones, kind of the other process. So first off, we want to determine whether or not there's sort of polar bonds here. They're nice enough to give us some electronegativity values. So if we look between, say, our oxygen and our nitrogen, we got 3.5 minus 3 gives us 0.5. We really don't even need that because, again, if you look on the periodic table, carbon, nitrogen, oxygen, fluorine, we see oxygen is further to the right and it's in the same period, which means pretty safe bet to know that is going to be a polar bond. Now, nitrogen, chlorine, you may be tempted to go, it's going to be a polar bond, but it does have that diagonal relationship that we can actually see when we look at the electronegativity values here between nitrogen and chlorine, and it actually is a difference of 0, right? So that's going to be 3 minus 3, which is 0 for nitrogen and chlorine, which means this is actually a non-polar bond that's happening here. So we get to the part where we're talking about there are polar bonds. There's definitely 3 or more atoms involved here. So we want to look at the molecular geometry. And obviously, in this case, it has 3 electron pairs, 1, 2, and 3. And it has 2 bonds, right? Double bond counts as 1 bond and 2 bonds. 3 electron pairs and 2 bonds means the molecular geometry is angular or bent, which basically means if we sort of draw this semi-correct and sort of thing, we sort of have this guy on the left-hand side pulling down, nobody else pulling the other way. You can kind of imagine if you just pulled down on one side, the whole thing would kind of move, and it would be a polar molecule in this case. And again, in this case, we do have dots. We have some different things. So you may want to look at the electronegativity values just to make sure, but it is going to be polar in this particular case. Any questions on that there? Now, let's say we look at the guy to the right, and the guy to the right, honestly, I could look at it and go, I do not see dots. I see everything on the outside is the same. I know that this is going to be a non-polar molecule because it is symmetrical. Can I verify that? Well, I can. I got a sulfur and oxygen bond here, which means sulfur is 2.5, oxygen is 3.5, which means the difference is 1, which means we do have polar bonds. We got everybody heading towards the oxygen in this particular case. So, okay, if I'm not convinced by my quick way of doing it, I do see polar bonds. The geometry here is 3 electron pairs and 3 bonds, which means this is trigonal planar. Trigonal planar is a triangle, basically, which basically means we have a triangle happening here. And at the corner of each triangle is an oxygen pulling equally, which means they are going to cancel each other out. And again, that's why it would be nonpolar in this case. Again, if you think about the rope example, kind of a triangle equal and opposite of each other's in the corners of an equilateral triangle gives you a nonpolar molecule. So again, an example that you definitely can have polar bonds, but because of the geometry here, they do cancel each other out. Also shows that if you just did it the quick way, you would get the right answer as well. So for the rest of these, that's sort of the approach I'm going to take, is sort of maybe the quicker way. I'm going to look at my Lewis structure and I see dots. I see everything on the outside is the same. That means it's going to be unsymmetrical, and this guy is going to be a polar molecule, because of that. And it is because it's angular as well. Again, both of the guys are going towards oxygen. So on sort of that angle, both kind of pulling down, the whole thing is going to kind of come down and become polar. I come here, I see central atom has dots. I see everybody on the outside is the same. I know this is going to be a polar molecule as well. Also contains polar bonds. The fluorine is more electronegative. Again, this is going to be our trigonal pyramid sort of geometry, much like what we saw with our NH3. And we're going to have those three sort of fluorines pulling and nobody pulling the other way. So kind of like three people kind of pulling in the same direction-ish, and nobody pulling back, going to cause some movement to occur, again, heading towards the fluorines in this case, making it a polar molecule. Now, I come over here, even though it has a charge, if we just do it based off of geometry, forgetting about the -2 charge, I look at my Lewis structure here for carbonate, and I see no dots. I see everything on the outside is the same, so no dots. That means that this is going to be non-polar molecule. So remember, no dots, everything on the outside the same, going to end up being non-polar. And that's because, again, this is a trigonal planar geometry, which means it's this triangle, which means at the corner of each of these triangle, we have the oxygens pulling equally, and they're going to cancel each other out and end up being non-polar. Following my same rule, I'm going to go no dots. Everything on the outside is the same. Also going to be non-polar here. Same reason, geometry here is also going to be triangular or trigonal planar, meaning that they're going to be equal and opposite of each other, pulling towards the fluorines in each of those cases. And lastly, no dots. Everybody on the outside is the same, going to be a non-polar molecule. Again, here they're going to be in the tetrahedral arrangement, equal and opposite of each other, all pulling towards the bromine. They do have polar bonds. So just to be clear, there's polar bonds in this guy, there's polar bonds in this guy, there's polar bonds in this guy. So there are individual polar bonds happening here and also here and so forth all the way across. But again, because of the geometry, it's going to cancel each other out and become a non-polar molecule overall. And again, if we were to swap out one of these bromines, like we talked about earlier, for say a hydrogen, this now would become a polar molecule, as we would have polar bonds heading to the bromine and our non-polar bond here with hydrogen and carbon. So basically, again, we now turned it into like three guys pulling versus one guy trying to hang on. It's going to kind of move and become polar. So to keep it simple in terms of molecular polarity, you know, that's really kind of the best way to do it is kind of dots or no dots. And you usually will be okay in terms of determining molecular polarity. But again, to keep in mind when we're talking about three or more guys involved, you can have polar bonds, but the molecule be nonpolar. So that is a situation. So you want to make sure that if you come across a question or something like that, if they're asking, is there polar bonds? That may be a different answer than is the molecule polar or nonpolar. So when you think about sort of the study assignment, the second to last column was type of bonds, which is asking, are there polar bonds or nonpolar bonds using like electronegativity like we see here and, you know, arrows. The last column in the study assignment says, is the molecule polar or nonpolar? Is asking what we just did here. Is the overall molecule polar or nonpolar based on all the bonds that are present and sort of the shape of the molecule? Again, the easiest one to determine in terms of molecular polarity is our diatomic molecules, because there's only one bond, which means if that bond is polar, molecule is polar. if that bond is nonpolar, molecule is nonpolar. Any questions on molecular polarity? And again, just an example here of how geometry plays into effect. If you had CO2 and for some reason you thought the geometry was bent or V-shaped, it would actually be a polar molecule. But what we know is this is not the correct geometry. The correct geometry is linear. And because of that geometry, it affects the overall polarity of it. Any questions on molecular polarity, Lewis structures, drawing, any of those things? So clearly at this point, you need to be able to do everything we've talked about in these last 2 chapters. Draw Lewis structures, calculate formal charge, determine electron geometry, determine molecular geometry, determine hybridization, determine whether or not the individual bond is polar or nonpolar, and now determine is the overall molecule polar or nonpolar, in addition to obviously understanding sigma bonds and pi bonds. Any questions on any of that stuff that we talked about? That is a lot to digest. All right, so a couple of things here. Because the exam is coming up shortly in a couple of weeks, I think we will do a quiz on all this fun stuff. Chapter 3 and 4, basically what I just mentioned: Lewis structures, formal charges, polarity, molecular geometry, electron pair geometry. We'll do it next Wednesday. Let's go with next Wednesday. Monday's the holiday for 4th of July, even though it's the 5th. And then Tuesday, then Wednesday. So I guess that would be 5, 6, I want to say 7. And I'll let you know when we'll do it, but pretty much maybe it'll be like we did before. We might do it during lab time or something like that, or start a lab. But it will be on chapter 3 and 4. Basically, it will be on, all the stuff that we've been talking about, the drawing the Lewis structures and all that kind of stuff. Kind of similar to study assignment B that you got going on right now. Any questions on that? Okay. So speaking of study assignment B, you should now definitely, I hope, be able to complete study assignment B. We will make that due tomorrow at the end of lab. So tomorrow at the end of lab, study assignment B will be due. That's July 1st tomorrow, 1st, 2nd, 3rd, yeah. So study assignment B, which should be our Lewis structures, will be due on 7/1 completed. Remember that you did need to add the electron pair geometry to that chart that you were doing. And then today you have due, if you haven't uploaded it yet, I saw some of you did already, the experiment 6 should be due today. And like I said, tomorrow we will probably start, obviously, experiment 7, and that should then take us back on track. We'll then get into probably